So how do we convert between different bases? Well, first, why do we convert between different bases? Because different bases are more useful in different situations. Base 10, decimal, well, that's for us humans. Hexadecimal, well, that's pretty easy. One hexadecimal digit represents 4 bits in a computer. Of course, binary, so binary is useful for computers, base 2. But base 16 hexadecimal, one digit represents 4 bits. And nowadays, computers have 8 bits in a byte. That didn't used to be true, but it is now. So every 2 hexadecimal digits is 1 byte. Nice and easy. Ever look at a MAC address, MAC address on a network card? Or the level codes in Super Mario Maker? Anytime you see a string of what looks like gibberish digits that just happens to include the letters A through F, that's probably going to be hexadecimal. As for octal, that's pretty much used in Unix for a specific thing and not terribly much else, because one octal digit happens to contain 3 bits. But anyway, we convert between different bases based on the situation. Now, you can convert directly from one base to another. The method I'm going to show you works between any 2 bases. But here's the thing, it's hard to do that math in your head. If you can just ask Google or you have a specific calculator to do it, use that. But if you ever have to do it on just a regular calculator, then there's a trick, because a regular calculator is going to use base 10 because it's based on us. You can convert from any base to any base. So you can go from a base to base 10 and then to another base. An extra step going either way, but you can do it on anything, including just writing it out by hand. And who doesn't have access to a base 10 calculator anyway? From your TI monstrosities to the one your grandpappy gave you when you were knee-high to a grasshopper. Every computer, every smartphone, many dumb phones, there's calculators everywhere, so this method will always be available to you. So it's very simple. If we have a number, we have the integral part, that's how many whole units, and the fractional part, that's the remaining portion of 1 unit, and the fractional part can be 0. When you convert bases, the integral part is the integral part and the fractional part is the fractional part. The decimal point, or the fraction point, whatever you want to call it, is in the same place. So we convert this and we convert this and we just paste them together again. So you can convert the integral part from a base to base 10 to a base from base 10, and you can convert the fractional part from a base to base 10 and to a base from base 10. Reminder, not every number can be represented in a finite number of digits in every base. 1 over 3 in base 10 is 0.333, repeating of course, and in base 3, so if you say 10, it's base 10, and in base 3, it's 0.1 in base 3. So when you convert from one to the other, you may be dealing with repeating digits, or you may suddenly create repeating digits. Also, you may not realize it. If you're using a calculator, it has only so many digits for the fractional part. It's got only so much precision. So if you're not careful, you can chop pieces off. If you're doing small numbers, it's fine, because the rounding happens way lower than any precision you've already got, so you just round again and you've got the same number. Or truncate, rather, not round. Or maybe round. Depends. What I'm saying is be careful. If you're only dealing with integers, which is the usual thing, you almost never are going to have fractional conversion into some other base. There's really not a reason to do that. Almost always. So when you're dealing with integers, there's no precision issues. It's always perfect. But here we go. So to save myself a headache, I have pre-computed the following. 2676.1054685 in base 10 is A74.1b in base 16. So this is decimal and this is hexadecimal. So 2676 is A74 and blah 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 is 1b as a fractional part. So let's start by converting from hexadecimal to decimal. A74. So we have 3 digits. It's A, which is 10, times 16 to the 2, plus 7 times 16 to the 1, plus 4 times 16 to the 0. We're not going to write it all out every time we get it. So what's the trick? First, we take the leftmost digit. It's 10. So our result, our running total, is 10. So far, we have 10. And now, we are done with this digit. We're done with A. If that was the only digit, then we're done. If it's just A, that's 10. But we have a 7 as the next digit. So we do times 16. And then we add 7. So basically we're shifting over and adding the next digit. Because in this digit, every one of them is worth 16. We have 7 times 1, but 10 times 16. That's why we do it. So if you put this in your calculator, you get 167. Then we do the same thing again. This is our new running total. We're down to 7, but we have another digit. So we take this again times 16, because everything over there was again worth 16 more, plus 4, and then the calculator gives us 2676. There it is. What did we do? A74. So let's write out what we did. We did 10 times 16 plus 7 times 16 plus 4. But if we distribute this 16 through, we get times 16 squared, and then times 16 here, and that goes away. Last digit is 16 to the 0, obviously, so we've got 16 to the 2, 16 to the 1, 16 to the 0, and there's the digits. So we start on the left. This is going to have the most number of 16 times 16 times 16, and then for each digit, we just add another multiply 16, and it kind of stair steps like that. That's why it works. So now we've converted the integral part to base 10. Now let's convert the fractional part. We kind of do the opposite. We have 1b, and it's 0.1b, of course. So we start on the right. Last time we started on the left, now we start on the right. It's always away from the decimal point. b, that's 11. So we have 11. And then divide by 16. Last time we started with the first digit and we didn't multiply by 16 yet. But this time we do. Because, see, the top digit is times 1, times 16 to the 0. But the digits over here, every single one of them already includes 16 to the negative 1, 16 to the minus 1, 16 to the minus 2. So we have to start with one of those. So 11 over 16, and then, if that was the last digit, we're done. But it's not, so we got to go one more. So we add 1, and then divide by 16. And you have to do the addition before the division. Remember your order of operations. We have to have the extra parentheses because we don't want to divide 1 into 16 yet. So again, last time we multiplied and then added. This time we add, then divide, because everything gets an extra division because it's over there. So what do? We have 11 divided by 16, so that's 11 times 16 to the minus 1. And then we add 1 plus 1, which would be times 16 to the 0. But then we divide both by 16, so that becomes minus 2, and that becomes minus 1. So we've got 1 times 16 to the minus 1 and 11 times 16 to the minus 2. And that comes out to this fraction. And there you go. Those were the easy ones. The rest aren't hard, they're just not quite as easy. Going from decimal to another base. So we start with 2676. The first thing you do is you take this and you say, what is this divided by 16? 2676 divided by 16 is 167.25. We have to split this apart. We're actually taking the remainder. So what you do on your calculator, right? This is the easy method. So you see this 167, you make a note of it. You make a note, so you say 167. We'll just write it down there. And then on your calculator, you do minus 167 to just get rid of it. So now you're left with just the 0.25. Now multiply the 16 back. Times 16 equals 4. So what we've done is we've taken 2676 and we have divided it by 16 and gotten all of the whole times it's divided by 16 and just the leftover, the remainder of 4. This is our first digit. There it is. So we got this one. There's our 4. Now we don't need the 0.25, we can get rid of it. We don't need any of this, in fact. We just need the 167. 167 divided by 16 equals 10.4375. So we make a note of that 10. Now we don't need the 10 anymore, so minus 10 times 16. And again, your precision on your calculator. I'm getting precise exact results because there's plenty of precision. It's, I would assume this is 64 bits. It's a decently expensive tablet. And your home computer is almost certainly going to be 64 bits, but be aware, if you're using an older basic one, it may not have enough precision. If you go too many digits, instead of doing this whole divide and then multiply again, you might just have to calculate the remainder, like 2676 equals, divided by 16, equals 167.25. So you might do like 167 times 16 equals 2672. 2672, and then 2676 minus 2672 is 4, so you can get your 4 that way, and then you're not dealing with any actual fractions. So the precision doesn't matter. You're dealing with just integers, if you have to. But for small numbers, this works perfectly well. So there you go. So we have the 10. We've written down the 10. We don't care. So we do minus 10, then we do times 16, and it comes out to 7. There's our 7. That's our next digit. Then we're left with 10, because we're done with all that. But 10 is less than 16. It's a single digit. It's A. There's our A, since it's small enough. And then, of course, you say, you know, can we have more? Yeah, if you divide this by 16, you get a result of 0 point whatever. And so you get a digit of, in this case 10, and then your result goes from 10 to 0, and then divide by 16, you get 0 and 0, 0.0, 0.0, so, you could have 0, 0, 0, 0. So it works. If you start adding zeros and you're not paying attention, that would be why. If you divide 0 by something, think about what you're doing. Anyway, that's how you convert that way. And I showed you the method of never actually using a fractional part if you want to 100% guarantee that you never have an issue with precision. Fractional part, of course, you have to do it. And you just have to make sure you have enough precision. So now the fun part. Let me type this in. 0.1054687.5. So if you have enough precision to put that in your calculator and you hit equals and it stays the same, you're probably good. So we do the opposite. This time we're multiplying by 16. So we take this 0.1054687.5 times 16 equals 1.6875. So we have our integral part and our fractional part. The integral part, this 1, there's your digit. If this was 11, then it would be a b. In this case, it's 1. There's our 1. So then you just do minus 1. You get rid of that because we don't need it. We have just 0.6875. So now you multiply by 16 again, and you get 11. How convenient. But if you had a fractional part, once again you would have a digit and then the running total, or anti-total, I guess, to get more and more digits. But in this case, there's a second digit, b is 11, and that's it. So why do these work? Well, 2676 equals 167 times 16 plus 4. That's all that I did in the calculator was separate the divisible and the remainder. 167 equals 10 times 16 plus 7. And of course, 10 equals 0 times 16 plus 10. And if we look here, we have 10, 7, 4. That's all we're doing. And the same thing for the fractional, just kind of in reverse. All 4 of these methods are kind of doing the same thing that positional notation does anyway. It's using the idea of digits to wrap up algebra so we don't actually have to do algebra. So now a quick summary, in case you missed the actual methods. To go from a base that's not 10 to a base that is 10, you multiply the first digit by the base and add the second digit. Multiply all that by the base, add the third digit, and there's your integral part. You take the last digit of the fractional part, divide by the base, add the next digit, divide by the base, and then you're done and you put them back together. To go from base 10 to any other base, you take the integral part, you divide by the base and you get the quotient and the remainder. The remainder is a digit. Then you take the quotient, do it again, get the new quotient and remainder. The remainder is a digit. Once your quotient becomes 0, there's nothing more to do. And the opposite for the fractional part. You multiply the fractional part by the base, the new base. You get a digit, strip it off, take the remaining fractional part, get a new digit, strip it off, until you're done. Or you have a repeating decimal, and you eventually get tired of writing down decimals or you run out of paper. This may not be useful for actually doing anymore. Back in my day, I actually would do this by hand because we didn't have things like Google. We didn't have fancy, well, I guess we did have fancy graphing calculators, but I didn't understand how to program them yet. This was all new to me. Even the internet was new to me back in the school days of yore. Nowadays you ask Google. But it's still good to understand, first of all, because it's good to understand things. And second, because sometimes you may want to write your own program to do this. This knowledge of base conversion actually is handy in my work on a base 256 big num library. There's all kinds of different ways to do big nums, and people have done it before, and you just download a big num library. If you don't know what big nums are, I'll tell you later. But I think I have my own twist on it that I'd like to explore. So while I do that, I'll be seeing you.